Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Now that we have a set of textures ready for our 3D model, we can update our pixel shader to sample from these textures. In today's video we are going to do a few bug fixes and update the pixel shader. In the next video, we'll update the C++ code in order to pass the script or indices to the pixel shader. Here we have our scene with the new model in it, and we have almost everything we need in order to render it with textures. The only thing that's missing is the information for the pixel shader, which needs to know what textures it has to sample from. Since we are using bindless resource technique, we can get any texture that we want by indexing into the resource descriptor heap. So what we are going to do in this episode is basically just channeling these indices through the engine and making them accessible by the pixel shader. Before we start though, I need to fix a few bugs which I caused in the last episode, the first one of which is a potentially never-ending for loop. Here we get the LOD index depending on some threshold value. We are using an unsigned integer for the loop's index and we are subtracting as long as it's greater or equals 0, and obviously it will cause it to wrap around and possibly hang the application if this threshold condition is never satisfied. To resolve this, we make it loop for as long as I is larger than 0, and by removing this assertion, we can always return the first LOD with index 0. Furthermore, this buffer variable is never used and we can remove it. The next issue is that the way we are formatting the texture data is not entirely correct. Although it works for 2D textures and texture arrays, it doesn't upload 3D textures to the GPU correctly. And that's because we are putting some data in between the depth slices of 3D textures. As you can see here in this method where texture data is written to a binary buffer, we put this information in between slices, and in case of 3D textures, the API expects that all the slices are placed contiguously in the buffer. We can fix it easily by moving this data in front of the slices and write it just once, since all slices have the same size anyway. We also never used the width and height values, so we only have to save the row and slice pitches. I'll update the data format description here to better reflect what's in the buffer. For each MIP level, we have as many slices as the depth for that MIP level. Let me quickly add an assertion here too. In the C++ side, this part of the function becomes simpler since we can get rid of this for loop now. This next one is not a bug per se, but it does increase the chances of a stack overflow since we only have 1 MB of stack buffer by default. We could configure the stack buffer to be larger of course, but I'd like to keep it at its default size for now. Therefore I'm just going to use heap allocation, which is totally fine since this is not a hot path anyway. So first we compute how much room we need and then allocate that many bytes from the heap. Then we can segment this buffer and set our pointers. And that's all. Let me also update this information everywhere else. The next one is an improvement that I apparently missed when I was decoupling PSO creation from the main execution path. Here we lock the array of render items and then try to create one or more PSOs, which could take a relatively long time. And in all that time we can't access render items, which we obviously need to for rendering. This could result in frame stutter, which is undesirable. Instead of locking the array here, we can create a local array of items and copy it after we are done creating the PSOs. So I'll place the lock after the for loop and stack allocate an array of the 3D12 render items. In the for loop, we simply fill this array instead of inserting the items right away. After all items were created, we can put them in render items array, which is rather quick. Please have a look at the create PSO function to get a more complete picture of how PSOs can be created asynchronously. The next one is a copy-paste error. This assertion checks if the item index is less than or equal to render item count while in the loop. However, when the loop exits, these values should be exactly equal. Forgot a parenthesis here. And fix a spelling typo. I think that's all of them. The application runs as before, which means we can continue. Oh, and I'll make this constructor explicit. Okay, now since our aim is to get a list of descriptor indices into our shader, that's where we can start working on next. This is our test shader, which I'm going to edit in Visual Studio 2019, since 2022 has a non-configurable code formatting for HLSL files, which I had to turn off entirely. Here I fix a typo and add a position only defined for completeness. And here is the main pixel shader where we use the interpolated normal vector for lighting calculations. I'll remove this factor that's dimming directional lights, which I did in order to be able to see the callable lights easier. Also, we are no longer hijacking the main directional light. Now the scene is a lot brighter, and I think it's because the light intensity is set to a value of 10. I'll set it to 1 again. Also, let's use fewer lights. We go from 64,000 lights to about 8,000 lights. Since we are here, I'll also add a for loop to remove disabled lights. This matters when we test the light interface, and I forgot to add it when we did that test. Oh wait, I wasn't running the correct build all this time. I couldn't see which build config was selected because of this wonderful formatting here. I mean, this right here is a giant indicator of how much Visual Studio developers care about this software, right? Anyway, switching to debug build reveals that we need to save our textures again, since we changed the data format and that's why it's causing a problem here. We don't need to re-import the textures, only load each one in order to save it for testing. Okay, now we have got our textures and we can run the application again. The point lights and spotlights look a bit faint now, and that's because we are still limiting their intensity here in the shader. I'm going to remove these a bit later. Since we are going to use additional material properties for rendering, I'm going to define a surface data structure which we can pass around instead of just the normal vector. This structure contains values for each of the properties used to determine how light interacts with the pixel. Most of them are quite obvious. In this episode, we are not using the metallic property because Wang shading doesn't directly support metallic objects. Perceptual roughness is a value between 0 and 1, and it will be mapped to a roughness value when we do physically based rendering. That's why I wanted to make a distinction between the two. We can write a function that takes in the output of the vertex shader for this pixel and returns a surface. For now, I'll just set a default value for each property. We can use the interpolated normal vector for surface normal. In the main pixel shader, instead of this normal variable, we can get a surface. Then we can pass it to all lighting functions. At the end, when all lights have been calculated, we multiply the resulting color with the ambient occlusion value and add the emissive color. Since we are going to start working on physically based rendering, I'll factor out the Wang lighting in a separate function which I'll call Wang BRDF, where BRDF stands for Bidirectional Reflectance Distribution Function. It's a fancy name for a function that calculates the intensity and color of the light that is reflected by a pixel with a given set of surface properties. I'll discuss BRDFs in a bit more detail in the following episodes. However, I'd like to recommend watching these videos if you'd like to prepare for the upcoming episodes. So this is just a copy of what we have here, but instead of using a random value of 4 for the shininess, we use a value that's based on the roughness, as we'll see shortly. In this lighting function, we call Wang BRDF, passing it the surface normal, light and view directions, and the base color. I'll use 1 for specular color. And the shininess value is 1 minus the perceptual roughness times 100. We multiply the result by the cosine of the angle between the light direction and the surface normal and divide it by pi. This is the light intensity, which we multiply by the light color to get the color of the reflected light. Together with the emissive part which we already added, they form the rendering equation. We don't have a constant for pi, so I have to add it next. We also need to pass the surface to other lighting functions. As I mentioned before, we don't need to dim the lights anymore. Let's see if it works. This should be a float, of course. Fix a spelling typo for perceptual roughness. And I forgot to define the end variable, which is the normal vector. The lights still look a bit too dim though, so let me find out why. Oh, this intensity is for colorful lights. I'm not sure why it has to be this intense though, but I think we'll figure it out sometime. I see there's also been a typo in this function's name all this time. Why you guys never tell me? Alright, that looks better. Now we are ready to receive texture indices. Here we'll add a new structured buffer of unsigned integers using shader register T2. If you'd look up the C++ code where we define the root signature for opaque objects, you'd see that we have a root parameter defined as a shader resource view using shader register number 2. Okay, let's suppose that we have a variation of our pixel shader that uses textures. Then we can sample from those textures in the getSurface function in order to determine the surface properties. Let me actually edit this in Visual Studio 2019. So if this shader is part of a textured material, then we can use the dynamic resource feature to directly index into the resource descriptor heap and fetch the texture. It looks a bit complicated, but let me explain. This part will access a shader resource view in the resource descriptor heap, which we set for the pipeline. We'll have to use an index that we know beforehand in order to get an SRV index from SRV indices buffer. We have been using this before in the post-process shader, for example, where we get the GPass main buffer in order to read its pixels. However, this time we need to use a sampler in order to read values from the texture that aren't necessarily at an integer pixel location. That's what this sample function is for, which requires a sampler object and a UV coordinate where it will sample the texture. I'll put this in its own function to make it easier to sample textures. For example, now we can sample the base color texture using a linear sampler. As we'll see in the next video, the texture is located at index 1 in the material, which we create in the C++ site. We are going to use a static sampler for linear sampling. There are two kinds of samplers in DirectX: dynamic samplers and static samplers. Dynamic samplers can only be accessed through a sampler descriptor heap, which is similar to a resource descriptor heap, except it contains sampler descriptors. Static samplers can be defined directly in the root signature and are therefore easier to use. We are going to add the samplers in the next video. For now, let's assume that we already have a linear sampler that we can use for sampling our textures. I'll also add a point sampler and an anisotropic sampler, although we are not going to use those here. I recommend reading this blog article about different kinds of samplers and their properties. Now we can just call the sample function with the index of each texture, the sampler, and the UV coordinate at which we would like to sample the texture. When we are going to define the material for this model in the next video, We'll put the ambient occlusion texture first, so its index within the SRV indices is 0. Then we put base color, emissive, metal rough and the normal map in that exact order. Since we need to put metallic and roughness values in separate properties, I'll sample it first and then use its red and green channels to set those values. We can also already sample the normal map, but we are not doing anything with it yet because we are going to implement normal mapping in the next episode. I forgot a bracket for the double indexing here. And we can run the application again. In the next video, we are going to define the static samplers and put them in the root signature. We are also going to get the SRV indices for our texture set and channel them through the GPass cache in order to get them to our pixel shader. Thank you as always for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!